We are researchers from University of Illinois Urbana-Champaign. We are glad to share our paper RMAM, which is one of the winners of VOTST challenge at ECCV 2024. We are also glad to notice that the winner solution also adopt our method. Our paper is accepted at CVPR 2024, where we demonstrate a new insights into improving video understanding. The key insights of our RMAM is to rethink the conventional approaches of managing memory banks. Take the example on the right where a person is manipulating the dose, and the VOS task is to track and segment the two doses in red and green. The conventional approach of expanding memory banks continuously appending the new frames into the memory banks. Although this method captures all the information, it complicates the deciphering of relevant features. On the contrary, we propose that restricted memory banks as on the below use a fixed size memory bank, and this improves VOS accuracy, especially on the challenging scenarios like long videos and state changes, which are both highlighted on this VOTST challenge. In this typical state change scenario, our restricted memory bank can precisely capture the objects, while the conventional approach cannot. Our investigation is different from previous studies in that we go beyond the mere efficiency advantages of restricted memory banks, but revealing their key advantages of VOS accuracy. And just for your information, such a restricted memory bank is also adopted in the most recent SAM2 model, so we think it could be a very powerful component for all the VOS methods. To review the negative impacts of memory bank sizes on finding and decoding the relevant features, we designed a pilot study called Memory Deciphering Analysis. To control the variables for this analysis, we mainly analyze how can we recover the masks of the first frame using the memory bank. Since the information of the first frame is always provided to the memory bank and stored throughout the whole video, the network should be able to decode the perfect mask of the first frame as the GT shown in this figure. However, this is not the case. We observe that VOS models cannot consistently decode the correct first frame mask under an expanding memory bank. As shown in this example, the decoded mask degrades significantly as the memory bank size becomes larger and larger from 4 frames to 32 frames. Suppose we bound the size of the memory bank. We can quantitatively observe that the quality of masks evaluated by the means of Jacquard can maintain the original performance without significant decrease, while an expanding memory bank shows steady drops. Therefore, we conclude that the size of memory bank greatly influences the VOS performance. To reflect our insights of the negative impact of a larger VOS memory bank, we design our methods RMAM accordingly. Our baseline is an encoder-decoder architecture of VOS methods like AOT, where the decoder using memory bank as the keys and values to generate the masks on the current frames. Our first modification is the direct implication of our insight, restricting the size of memory banks with a constant number. As a baseline, we select the first frame, which is the input to the VOS, and the most recent K-1 frames, similar to a first in, first out schedule. Our second innovation is to develop a special algorithm selecting the frames in the memory banks. Our intuition is to keep the most relevant frames to provide the information while keeping most up-to-date information via the freshness. So basically, we are balancing the two terms of relevance and freshness when we select the features in the memory bank. In our paper, we explain in detail about how we use multi-arm bandits to design the balance of these two terms. please refer to our paper for details. Finally, our restricted memory banks significantly decrease the training inference gaps of memory bank sizes, since in our way, the length of memory banks won't grow without limits. To illustrate how this can impact the design space of VOS methods, we designed the temporal positional embedding to enhance the temporal reasoning of VOS methods. Specifically, we will design a set of learnable positional embedding to be appended to the memory bank features, so that the VOS methods are aware of the temporal order of the features. Just to highlight, this is the first ever temporal positional embeddings for VOS methods. On the challenging benchmark of VOST, which is also used in this challenge, we conduct the ablation study analyzing the effectiveness of our method. From a baseline of AOT, we can see that each proposed component effectively improves the performance. Notably, simply bounding the memory bank size is already a plug-and-play improvement for existing VOS methods, which is one of the key insights of our paper. Our RMM also becomes the new state-of-the-art on long videos and state changes. So in terms of this challenge, we mainly illustrate the performance on the left, where we improve DEAOT on the challenging VOST dataset. To provide more information, we also highlight that our method is very effective when dealing with very long videos, although we are using a much smaller memory bank. So here are the key takeaways of our method. We introduced the novel memory deciphering analysis to review the drawbacks of expanding memory banks. And based on this insight, we designed restricted memory banks to enhance VOS, especially for the challenging scenarios like state changes and long videos, which are both highlighted in this workshop. Benefiting from a smaller training and inference gaps, we also proposed the first ever temporal positional embedding to improve VOS, which we think is very significant for this workshop as well, because we need to understand the temporal order when we understand very challenging videos. In this QR code, we put our project website and codes. Please scan the QR code and access our paper if it is interesting. Thank you so much.